let's suppose that U1 and U2 are subspaces of some vector space V, so that you can define the sum of the subspaces. And if you want to know the dimension of these subspaces, then this is how you get it. Now, one immediate corollary of this is that if this is the direct sum of two vectors, two subspaces, if it's a direct sum of two subspaces, then it will be dimension of U1 and dimension of U2. If you have a direct sum, what's the intersection?
0.
0. So in that case, this value will be 0. So for the case of direct sum, it will just simply be addition of the dimension of each individual subspaces. That's what it means, right? So let's say let U1 through UM be the basis for U1 intersection U2. And this is possible because we already proved that U1 intersect U2 is a subspace. And we also proved last time that if you have any linearly independent list, then you can extend it as a basis. So you can say, since U1 through UM is linearly independent, well, not only are these linearly independent and U1 intersect U2, this is also in each one of them. See, if something belongs to each set in an intersection, no. If something belongs to intersection, then that thing belongs to each of these sets, right? So since this is these U1 through UM belong to this as a set, okay? These are elements in this set. These are also elements in U1, and these are also elements in U2. And because being a basis means it's linearly independent, this will be linearly independent in U1, and it will also be linearly independent in U2, okay? So any linearly independent list can be extended this list can be extended to a basis, and let's just say U1 through UM, then V1 through VK for U1, okay? So U1 through UM is a linearly independent list in U1, so extend this to the list, the list of bases for U1. Not the basis, but a basis. Keep saying the basis. There are infinitely many different possible bases for a vector space, right? Unless it's the null space. If it's not the null space, but if it's a trivial space, if it only has 0, then by definition you have an empty list, okay? But otherwise, any positive dimensional vector space has infinitely many different possible bases. So I can't say the basis. I should always say a basis. Okay, so now let me ask the following question. What is the dimension of U1?
M plus K.
Right, because this much is length M, this length is K, so the total length of this list is M plus K. So that's the dimension, because by definition, the dimension of a base, the dimension of a vector space is the length of any of its bases. Okay? Now, same way, we extend u1 through um to a basis u1 through um, and then let's say w1 through wj for u2. So that dimension of u2 is, same question, n plus j. Now, since we know the dimension of u1, dimension of u2, and dimension of u1 intersect u2, which is just m, this allows us to calculate the right side. So let's see what that is. Dimension of u1 plus dimension of u2 minus dimension of u1 intersect u2. So note that this is equal to m plus k plus m plus j minus m, so this is m plus k plus j. Okay. So that if we prove dimension of u1 plus u2 is equal to m plus k plus j, then we are done. We are done. Now, how do we prove that the dimension of u1 plus u2 is m plus k plus j? Well, because the definition of a dimension is the length of the basis, length of a basis, we just have to find a basis that's of this length. Okay. Can you guess what that would be? What's a list that's length m here?
u1 through un.
What's a list that's length k?
v1 through vk.
Yeah. And then
w1 through
w1 through wj. So what are we trying to say? Claim is a basis. Okay. What are two things that you have to show in order to show it's a basis?
linearly independent and spans a space.
Yeah. Okay, so let's first think about the span. So first, number one, span. Well, any v in u1 plus u2 is of the form I'll say, gee, I'm running out of letters. I already use U and W. I'll just use U and W. Hopefully it's not going to confuse people. So U plus W with U in U1 and W in U2. Right? That's the definition, right? What is this? What is this set? It's collection of all the possible vectors you can make by taking one element from here another element here, and you take the sum of it. You take everything that looks like this, collect it as a set, and at the end of the day, you can show that it's a subspace, right? So that's what it means to be the sum of two subspaces. But then we already agreed that since u1 through um and then v1 through vk is a basis for u1 and u is from u1, we have that u equals to something times u1, something times u2, sorry, a2, da 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 am um plus b1 v1 da 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 bk vk for sum a1 through am, b1 through bk in the base base field. Okay, likewise, you can say the same thing for w, right? This will be c1 u1, cm um, d1 w1 dj wj, right? And hence u plus w is equal to a1 plus c1 u1 am plus cm um plus b1 v1 bk vk plus d1 w1 dj wk, which is in the span of this guy, right? And by the way, these are vectors that belong in u plus w, so span of this is included. So that portion is usually trivial, you don't have to show that. As long as you can show that something, an arbitrary element that's from here is in the span, then you're done. Okay, so the equality is shown. So now you see that u plus w is indeed span of u1 through um, v1 through vk, and then w1 through wg. Okay, so span part is done. What's the second part again?
Linear independence.
Linear independence. So let's try to show that one. For two, linear independence. To show that, suppose a1, u1, all the way up till a m um plus b1 v1 all the way up till bk vk plus c1 w1 through cj wj is equal to 0. Okay. Our goal is to show that all the coefficients are 0. Right? a1 u1 plus da 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 am um plus b1 v1 move all the w's to the other side, so it's negative c1 w1 minus da 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 minus cj wj. So first of all, the left side is in u1 because u1 through um and v1 through vk span the entire u1. It's a basis for u1. And also u1 through um and then w1 through wj spans u2. So this right side goes into u2. Now what that means is that right side, negative c1 w1, is in u1 intersection u2, but remember u1 through um is the basis for u1 intersection u2, right? So we know that negative c1 w1 cj wj is equal to d1 u1 d2 u2 and then da 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 dm um. But wait, now we move this to the right side and we get 0 equals to d1 u1 plus d2 u2. Oh, let's not write down d2 u2. Da 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 plus dm um plus c1 w1 da 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 cj wj. So that's equal to 0, but that's 0 in where? This is in u2, right? Because anything that's in u2 is spanned by these vectors. Furthermore, this is a basis. u1 through um, w1 through wj is a basis, so since it's a basis inside u2, if it's equal to 0, there's only one way that can be done, right? All of these should be 0, right? So that tells you that d1 is 0, d2 is 0, all the way up till dm equal to 0, and then c1 0, c2 is 0, all the way up till cj equal to 0, right? That shows that c1 through cj is 0, right? Now you do the opposite. You move the here and then move the b1 through bk to the other side to make it negative b1 v1 through that. So the same argument can be used to show b1 through bk will be 0. So likewise, we can say a1 u1 through am um. Well, I guess we don't have to do that because we don't have to say likewise. Plug in these to the other side, then what do you get? So when these c values are plugged in on the right side, now we have this equal to 0, right? But u1 through um and v1 through vk are linearly independent in u1, right? So that says that the only way that this is possible if you have a1 is 0, all the way up till am is 0, b1 is 0, all the way up till bk is 0. So since we've shown all of these coefficients are 0, linear independence is proved. Okay. Since we finished proving that u1 through um, v1 through vk, and w1 through wj spans the entire u1 plus u2, and also are linearly independent, we've shown that this forms a basis and we're done. Okay? So the proof is complete. 1 and 2 shows that u1 through um, v1 through vk, w1 through wj is a basis for u1 plus u2, and the proof is complete. Okay? Let's write down QED to show that the proof is done.